Hi, today we are looking at section 5.1 and our notes for that, which is using fundamental trig identities. We have been working in the basic trig unit. We have learned and spent a lot of time learning the angles of the unit circle, right triangle trig, all of those kind of things, solving. And then we spent quite a bit of time going over graphing and inverse graphs and knowing that we have to have that marker on our graph for inverse graphs. So now we're shifting into what we call analytical trig, which is where we're going to start working with those identities. So if you remember the help sheet that I told you would be a good idea if you printed earlier in the year, when we first started the basic trig step, the back side of that is where you'll find all of the identities that we're going to be talking about. So right here at the top, I kind of have a summary. In this lesson, we're going to be looking at factoring, simplifying, replacing with trig identities, working with an algebraic identity, rewrite logs using properties, combine fractions with a common denominator. And I'm going to use a variety of techniques, so you'll have them and have seen how different ones work for different problems. That doesn't mean it's the only way that you can work the problem. Different techniques could work on the same problem. I'm just kind of trying to do as many different techniques as I can, so you can see how some of the options you have will work. So if you're working a problem and it ends up working out differently than a particular problem in the notes has worked out, it doesn't mean it's wrong. It just means that's the problem I chose to show you that technique on. The new values introduced in the problem must be a known trig identity or an algebraic identity. So we are not solving, we're not dividing both sides by a trig function or any of that stuff. We have to simply replace and simplify. Algebraic operations used to solve equations, they don't work for trig identities. And what we're doing today is not proving or verifying, we're just simplifying. In a problem, all terms must be in the same trig identity if you want to be able to factor. So if they're not all in the same trig identity, then you're going to use an identity, make a replacement, and then you should be able to factor. And you're only going to use one equal sign per line, and our steps, as always, should be running vertically, not side to side. So here is the notes that you will see in the note sheet that's attached online. We have a section right here where it says for this section you need to memorize these identities. So that's the reciprocal and the quotient. So I went ahead and just kind of took a screenshot of that part of that help sheet that I told you you had. And so you should already have reciprocal and quotient identities memorized from what we did in chapter 4 as well as the Pythagorean identities. So really it's just these two sets that you're going to kind of have to focus on if you've been keeping up. And that's the even and odd identities and the cofunction identities, or complementary angles as we called them earlier. So these are all the identities that we're working from. These are all the identities we're working on getting committed to memory. And we're going to use these identities as we work through these 8 examples. So let's start with the first one. The first one is simplify sine of x cosine squared x minus sine of x. When we simplify, this right here is the problem. So you have your equal sign at the end of your problem. This is where I started working. So you can see that I have the equal sign right here in front because these are my steps, one step per line. And so the first thing I did was said, okay, well, we've got sine, cosine, those are different identities. And if it has a power of 2, then I know I'm working with the Pythagorean identity. So I replaced cosine squared x with 1 minus sine squared x. And now notice everything is in the same trig function. So that's what I mean by replaced with an identity. I took cosine squared x, I replaced it with the other side of the identity. Then I have to distribute sine through. And so what I have is sine of x minus sine cubed x, because 1 sine x times 2 of them, you would add the exponents together. So that gives you that 3, and then minus sine x. So remember, we would be looking left to right, and I could see a sine x minus sine x back here. I am okay to mark them out when I'm simplifying. I am not okay to do that when I'm proving. When I'm proving, you need to move them together and show that those two things would make a 0, but we're not there yet. That's 5, 2. So these two things are going to cancel, and I'm left with negative sine cubed x, and that's my final answer. Notice the way I have my work set up. When I get down to the bottom, it's very clear in my work what my answer is. No one should have to hunt for it. No one should have to go looking sideways across your paper for it. Everything should be nice and neatly organized. By now in the year, that should not be an issue, and yet some of you are still struggling with that. So make sure you're working on good form here, because we will be proving things, and that's going to be even more important to have good form. The next set of problems on 2 is about factoring. So remember I said earlier that we would be factoring and that you needed to have all of the same trig function, so you can't factor when there's a sine and a cosine in the problem, okay? So the first one, 2a, if you're looking at this is sine squared theta minus 1. You can think x squared minus 1. You can't write x plus 1, x minus 1. What I'm trying to factor is secant, not x. But if this helps you to recognize, oh, well, that's just the difference of squares, which means I have one binomial with a plus sign and one binomial with a minus sign, then you can do that. This is great mental help. It's just not what we want to see in your paper. So be real careful about the use of the correct unit. The second one, for tangent squared theta plus tan theta equal minus 3. Notice there's no equal sign, we're just factoring. And so if I think about this as 4x squared plus x minus 3, in other words, if I take and make tangent x, then I have 4x squared plus x minus 3. So basically that's a trinomial with a leading coefficient other than 1. So you would need one of your strategies, cab, box, factor by grouping, all of those things. And so then I would have two factors, tan theta plus 1 for tan theta minus 3. So again, for now, if you need to think about this in terms of x, kind of work out what that would look like in x and then transfer that back to tangent, you can. But the ultimate goal is that you can factor in trig functions and not have to waste all of that time right over here. But this is helpful for right now as you're kind of working your way through it. On C, I have cosecant squared x minus cotan x minus 3. Notice these are not the same trig function, so I can't readily factor. I have to make them all the same trig function. And because this is a power of 2, I know that I'm working with a Pythagorean identity. So I'm going to replace cosecant squared x with 1 plus cotan squared x. Now everything's in the same unit. So I'm going to combine my like terms because that's 1 plus cotan squared x minus cotan x minus 3. So I'm going to bring my cotan squared x up front. I'm going to bring my cotan next, and then I have 1 minus 3, which gives me negative 2. Now I have what looks like a normal trinomial, so I can think of it as x squared minus x minus 2, which means in terms of cotan, it's cotan x minus 2 times cotan x plus 1, and that is my factorization. So problem 2 kind of gives you 3 examples of factoring, and that's all we were doing was just factoring. All right, on number 3, we have simplifying as our directions. That means we can replace and simplify until I can simplify no further. The problem is sine of x plus cotan x cosine x. I am not in the same trig units, so I can't factor. But I'm going to take cotan x and change it into cosine x over sine x. That is my quotient identity. So I replaced this one with the quotient identity. Now I have this problem right here. So I just went ahead and turned that into a fraction because I know when I multiply fractions, I multiply the top and then I multiply the bottom. So now I have sine x plus cosine squared x over sine x. The two different pieces need to be combined, and the way we combined fractions is to have like terms. We have to have like denominators. So you can think of this, we used an acronym earlier in the year. If you're some of my students, I always say SMILE. That's a really shortcut way of multiplying, multiply, 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 make your little smile sign. But really that's just the fancy way of saying get a common denominator. Well, I don't know that it's fancy, but that's a little shortcut memory device for saying get a common denominator. So you would multiply the top and the bottom of this, because remember technically that would be over 1. So we would multiply the bottom 1 times sine x to get that common denominator, which means I also have to multiply the top. So sine x times sine x, remember, is just sine x squared. So now once I have my common denominator, then we know we have a single common denominator, not 2 sine x. I do see that from students. So remember, common denominator means the denominator's common, not that it's 2 of them. And then on the top I have sine squared x plus cosine squared x. And hopefully you recognize that this is an identity you already should have memorized, which is a Pythagorean identity. So sine squared x plus cosine squared x is 1 over sine. So I replace with Pythagorean identity. And now I have 1 over sine x, which is a reciprocal identity. So I'm going to replace it with the reciprocal identity, and that's going to leave me with cosecant x. And that's my final answer. Hopefully you're doing okay and we're in a good thumbs up position, or at least thumbs sideways maybe because you need a little more time. But hopefully we're in thumbs up or thumbs sideways. All right, let's move on to 3b. In 3b, we start with a fraction that has 1 plus cosine theta, and we have another fraction that has a denominator of sine. So when I have two fractions like this, my strategy has to be to get them together as a single fraction, because ultimately, remember, I'm trying to use my identities to make it simpler. All right, so common denominator is going to be 1 plus cosine theta and sine theta. Again, for my folks, that's a smile situation. So I multiply here and I get sine x theta times sine x theta. I multiply here and I get cosine theta times 1 plus cosine theta. Typically speaking, I always put the monomial in front whenever I do that, just because it's easier to see if I get in a habit of putting it in the same way. But basically what I did to get my common denominator, if I didn't smile, was I multiplied the top and the bottom of this fraction by sine theta, and the bottom and the top of this fraction by 1 plus cosine theta. So that's what you're seeing here and here. Now again, once I combine my numerator, so sine theta times sine theta is sine squared theta, cosine times 1 is cosine, cosine times cosine is cosine squared theta. In simplifying, we do not have to move the two pieces together to show the identity. We know that this is the Pythagorean identity, so I'm going to replace it with a 1 because sine squared theta plus cosine squared theta is 1. And that leaves me with plus cosine theta. Well, now you can see I have a numerator that is 1 plus cosine theta, and I have a factor in the denominator that's 1 plus cosine theta. So when these two things cancel, I'm left with 1 over sine theta. So what I did here was simplify, and now I have a reciprocal identity. So then I can use my reciprocal identity, replace with my reciprocal identity, and I get cosecant theta, and that's my final answer. So you can see I started up here with two fractions, I ended up down here with a single term. So that's that process of making things simpler. All right, so I hope we're still doing good. We're on number 4, okay? In number 4, we have to rewrite this log expression as a single log. So that rewrite as a single log should be your memory jog. That means you're going to have to use your log properties, your condensing properties, and so we're going to condense this down. So what I'm doing when I use my condensing rules is I'm looking to see how it's connected. In this case, it's connected with a plus sign, so I know my condensing rule means that I'm going to take what's inside my log and I'm going to multiply it together. Okay, so here's the original problem. So the first thing I'm going to do is rewrite it. And I rewrite it using the log property rule. Its connector is a plus sign, so that means I take this and I multiply it together. So I have condensed the addition with multiplication. All right, so now I have to start figuring out how to put this together. So to put this together, I'm going to use some identity replacement. I'm going to replace cosecant theta with its reciprocal identity. And I'm going to replace tan theta with its quotient identity. And the reason I chose those two to use is right here. You see how there's a denominator with sine theta and a numerator with sine theta. Well, that means those are going to cancel, and that's going to make my thing simpler. So remember, that's what we're trying to do is simplify. So I have, if I multiply the tops together, I get sine theta. If I multiply the bottoms together, I get sine theta, cosine theta, all within those absolute value bars. And anything divided by itself is 1. That's a simplifying rule. So now inside, I'm left with 1 over cosine theta. Well, 1 over cosine theta is a reciprocal identity, so I can replace this fraction with its reciprocal identity of secant theta, and now I have simplified that one. All right, we're halfway through. Hope we're doing good. All right, we're going to shift gears a little bit, and we're going to do a little evaluating. We did this in our last unit, so this shouldn't be too terribly difficult, except we are going to use an identity. That's the difference. But we're going to evaluate the 6 trig functions. That means in the end, I'm going to have an answer for sine, tangent, cotan, cosecant, secant, and cotan. And we are given sine of negative x equals negative 1/3, and tangent of x equals negative root 2 over 4. So I usually tell people you're going to start with this because we know a lot of times tangent is sine divided by cosine, and there's probably some simplifying that's going on. And I will check this along the way, but I'm actually going to work from here, and I'm going to use that odd even identity, because that right in there is negative. So the identity is negative sine x equals sine negative x. You can look at your identity sheet for right now if you need to. And so that means this piece right here, which is what I have here, is equal to negative sine x. So when I replace my identity, I'm going to substitute. Remember, we can replace and simplify. So I'm going to replace sine negative x with negative sine x, because that's the other side to the identity. And then I have a negative 3 over here. Well, we know that we need to work with positive trig functions. So I divide both sides by negative 1, and now I have sine of x equals 1/3. So all of this here was just using that identity. All right, so now we have to think like we did before. What quadrants will sine be positive? And that's going to be in 1 and 2. And then remember, tangent is negative up here, so what quadrants is tangent in when it's negative? And that's quadrant 2 and 4. So the one that they have in common is quadrant 2, and that's where I draw my triangle. So I'm going to use sine to lay out my triangle because that's the nice easy one. It's just opposite over hypotenuse. So there's my 1 and there's my 3, and I don't have to worry about a negative because those are both positive values, because this is graphing up, which is positive, and the hypotenuse is always positive. So real quickly, I'm going to use my Pythagorean theorem, and I'm going to get negative 2 root 2. So at this point, you can check. You can say, okay, would this really be negative root 2 over 2? And would I get this tangent? So I can go in my triangle and find tangent. And when I find tangent in my triangle, I do get negative root 2 over 4. So I know I'm good to go from there. So then it's just a matter of answering my 6 ratios. So remember your SOHCAHTOA. We already know sine. We already know tangent. So all we need to do is come up with these 4. So remember, cosine would be adjacent over hypotenuse. So this is adjacent, this is hypotenuse, so that gives me that. Cosecant of x is hypotenuse over opposite. So hypotenuse over opposite, so that gives me a nice pretty 3. Secant is hypotenuse over adjacent, so hypotenuse over adjacent, and then we would take care of that negative root 2 in the bottom. So you end up with negative 3 root 2 over 4. That's just rationalizing. So I'd multiply the bottom and the top by root 2 and simplify. And then cotan is adjacent over opposite. So here is adjacent, here's opposite. So that is nice negative 2 root 2. And so I have evaluated for all 6 trig functions. Okay, so for number 6, again, we're simplifying. So pay attention to the direction that it's giving you, what it's asking you to do, and what you're actually working through the problem with. So we are simplifying tangent squared theta over secant squared theta. So here's my problem. And this is a technique of separating the numerator in the fraction from the fraction. So sometimes it can be beneficial if we're able to pull this numerator off and pull it in front. And this is a legitimate technique to use because, again, we haven't done any operational kinds of things. We're not trying to solve or balance an equation. And we know that if I put a 1 over this, tan squared theta over 1, and multiplied it to 1 over secant squared theta, I would be right back where I started, which is tan squared theta over secant squared theta. So this is a technique of pulling the numerator from the top of the fraction. So once I do that, I went from having a single fraction that I'm trying to simplify to 2 pieces to work from, and that usually gives us a little more option as to how to proceed. So since this is tan squared theta, remember that just means tan theta times tan theta. So then that means sine theta over cosine theta times sine theta over cosine theta, which means sine squared theta over cosine squared theta. So this isn't math magic, it's just because there's two of them right there. So that means when you replace the identity, you have two fractions. All right, and we haven't done anything with this fraction. So now that's very handy because look again, we have a sine squared theta in the top and a sine squared theta in the bottom. So we know we're going to have some cancelization going on, and that's exactly what we might want to do if sine and secant, right? If they're the same. I pointed that out a minute ago and kind of went with it to see if you caught that, because that's a really common thing that happens sometimes when people are rushing, is they'll cancel a cosine with a cosecant or a sine with a secant. So just pay special attention and don't fall in that trap. All right, so this is 1 over secant squared theta, so I'm going to use that reciprocal identity. Remember, there's two secants in the bottom, so now there's going to be two cosines on top. And now we can do the simplifying we were talking about a minute ago, because this cosine is exactly the same as this cosine. There's two of them up here, two of them down there, so I can cancel. And then I'm left with sine squared theta. Now remember, this is simplifying, so I'm not having to move these together and show something divided by itself. I can do this little mark out thing here because I'm simplifying. We typically don't do mark outs like that when we're actually doing a proof. And remember, anytime you have something divided by itself, it's 1. Okay? So moving on to number 7. On number 7, we are simplifying again, so that makes it simple, means you're replacing and simplifying, replacing and simplifying. And in this case, the technique we're looking at is greatest common factor factoring. Notice there's a plus sign. We have cosine squared x on this side of the plus sign and cosine squared x on that side of the plus sign. So I am going to, remember, here's my problem. This is what it said to do. So I have my equal sign to start my work. And I have a cosine squared theta. I'm going to divide out of both pieces. So I'm cosine squared theta, bringing that out. And cosine squared theta divided by cosine squared theta gives me this 1 that's left over. And then when I divide out cosine squared theta here, cosine squared theta divided by cosine squared theta is 1, but it's 1 times tangent squared x. So you have this quantity left. So this is me pulling out the GCF, and the GCF, remember, was cosine squared theta x, which is what you divide out. All right, so I see the power of 2. I see this 1 plus tan. That should send flags up in my brain that this is a Pythagorean identity. So I go look up my Pythagorean identity in my brain, hopefully, because I have it memorized, and I know that that's secant squared x. All right, I haven't done anything here. That's still there. It was multiplied to this, so it's still multiplication. I replaced my identity with a Pythagorean identity right there. And so now I'm going to use my replacement identity again, because this, I'm going to use its reciprocal. Why am I going to use its reciprocal? Because I noticed over here that I had a cosine squared theta, and when I use the reciprocal, I know I'm going to have a cosine squared theta down here. So again, these two things are going to cancel, which means the reason they cancel is because when I do cosine squared x times 1, I get cosine squared x. And when I do 1 times cosine squared x, I get cosine squared x. So something divided by itself is 1. You could have went from here, used your mark out, and went straight down here. That's fine. I did it this way just so you kind of have a little foreshadowing of what it comes when it comes next, because this would be an example of definitely a step you would have to have in a proof or verify statement. You would have to show that you have something divided by itself. Here we just know it, and because we're simplifying, that's okay. All right, last one, folks. So we're starting out with two fractions, and we said earlier in the process when we have two fractions, we want to put it together and make one fraction. So I need a common denominator. So for my folks, that's a smile. You would do cosine x times cosine x, 1 plus sine x times 1 plus sine x, and then cosine x times 1 plus sine x. If you're getting a common denominator, then you would multiply the bottom and the top of this one by cosine x, and the bottom and the top of this one by 1 plus sine x. So however you need to do that to get you to this point is what you're trying to do. Okay, So once we have our common denominator right here, we have our new numerators. We need to clean up the top a little bit. And so that means cosine x times cosine x, which gives me my cosine squared x. And then on this side, we have to FOIL because we have two binomials. So 1 times 1 is 1. 1 times sine x plus 1 times sine x gives me 2 sine x. And then sine x times sine x is sine squared x. So once we've kind of cleaned this up a little bit, we're looking again at simplifying. So remember, I have part of my Pythagorean identity here plus part of my Pythagorean identity here. So I can replace these two pieces with that one right here. Remember, this is okay to do it this way because we are simplifying. When we get into verifying, you'd move these two pieces together to show it is the Pythagorean identity that's fully intact, so then you could go to 1. So I'm left with a 1, and I'm left with a 2 sine x. On the bottom, don't get over happy to simplify this because oftentimes when you're simplifying, you might have one of these factors in the problem along the way, and if you've went ahead and distributed and did that from the very beginning, then at some point you're probably going to have to undistribute and pull it back apart. So I always tell folks when you're doing these identity problems and working with identities, don't get overzealous here. Just leave it factored until the very end and then put it together if you need to do so. Okay, so we know simplifying, we can simplify and replace the identity like that. So now we're going to collect our like terms. So 1 plus 1 is 2 plus 2 sine x. Nothing's going on the bottom. It's still hanging out down there just like it was once we got our common denominator. So hopefully you see this situation right here again. You have a plus sign, you have one term in front of it, one term behind it, and they have a common factor of 2. So what is it you're going to do? You are going to take out the GCF. The GCF is 2, so I divide 2 by 2 and I get 1. And then I divide 2 sine x by 2 and I get sine x. I cannot emphasize enough how many people mess this up and just say there's a sine x left. And if you do that, you are messing up your entire answer. So you need to remember you're dividing everything by 2. Okay, so once you have your 2 out here, then you can see I left this factored and you can see that I have 1 plus sine x in the top and bottom. And so that means I can simplify 1 plus sine x. I can get rid of that. And once I get rid of that, I'm left with 2 over cosine x. And then I'm going to pull that numerator off again. Remember that technique we just talked about. And so I have 2 times 1 over cosine x. 1 over cosine x is a reciprocal identity, so I'm going to replace with my identity. And then I'm left with 2 times secant x, and that's my final answer. So hopefully you get the idea. Lots of replace and simplify, replace and simplify. Remember that you're not going to factor with anything that has more than one trig function. And we're probably in a point where you're not going to be super paper conscious. If you're going to do more than one proof, then I would do it down this way and then come over here and do another one over here. I'm sorry, not proof, simplifying if it's very long, because you're not going to have all of this explanation over here on the side. All right, guys, I hope that helps, and we will be back next time to learn about actually proving or verifying trig identities. So remember, everything today is simplifying. When we get into 5.2, that's when we start doing our trig proofs. Thanks, guys.